for the content overview, we'll go through introduction, linear model, quadratic model, cubic model, and the conclusion. Introduction. So I will be talking about the relationship between total cases and total death of people who have dengue fever through the number of the weeks. So dengue fever continues to affect many people across Malaysia, and its impact can change from weeks to weeks. This report looks at the number of the dengue cases and related death during the first 20 weeks of 2024. As the number of cases goes up and down, we also see similar changes in the number of the deaths. This pattern suggests that when more people get dengue, the risk of fatal outcome may also increase. Understanding this connection can help us take better steps to protect communities and save lives. As we all know, for the formula of linear model is y equals to a plus bx. We must follow these steps to solve this question. First, we represent this matrix of the above system as you can see in this slide. After that, we form the normal equation by using matrix transpose times matrix V equals to matrix transpose times Y. So after that, we will get the least square solution by using V equals to matrix transpose M inverse times with matrix transpose Y. So after that, we will get the best fit linear curve. So for the error vector, we must use this formula E equals to Y minus MV to get the error vector. Then we will get the answer will be 7.972299356 for the error vector. Next slide shows the graph of best fit curve against observed data and error vector against x value.
Now let's moving forward to quadratic model. In this presentation, I will cover the mathematical formulation of the quadratic model, the step-by-step process of deriving the best fit quadratic curve using the least squares method, and in-depth analysis of the quadratic graph and its implications. Our goal was to model the relationship between the total number of dengue cases, our independent variable which is x, and the total number of deaths, our dependent variable which is y. For this, we choose a quadratic model of the form y equals to a plus bx plus cx squared. Here, a is the y-intercept representing the baseline number of deaths when cases are 0. B is the linear coefficient indicating how deaths change with each additional case. C is the quadratic coefficient capturing any curvature in the relationship. To fit this model to our data, we use the least squares method, which minimizes the sum of square differences between the observed deaths and the deaths predicted by our model. We represented the problem in matrix forms as MV equals to Y, where M is the design matrix with columns for X, X1, and X2. V is the vector of coefficients A, B, C transpose. Y is the vector of observed deaths. Here is how the matrix M looks for our data set. Each row corresponds to a week and the columns represents the constant term, the number of cases, and the square of the number of cases respectively. So how to solve the quadratic model using least squares? To solve for the coefficient A, B, and C, we use the normal equations M transpose MV equals to M transpose Y. To compute M transpose M, this is a 3x3 matrix where each entry is the dot product of the corresponding columns of M. For example, the top left entry is the sum of squares of the first column, which is simply the number of data points 20. To compute M transpose Y, this is a vector where each entry is the dot product of a column of M with the vector Y. And lastly, to solve for B, we then solve the system M transpose M, V equals to M transpose Y to find the coefficient. This involves inverting M transpose M and multiplying it with M transpose Y. The final coefficient we obtained were A equals to negative 1.8, B equals to 0.0147, C equals to negative 2.57 times with 10 power of negative 6. Thus, our best fit quadratic equation is y equals to negative 1.8 plus 0.0147x minus with 2.57 times with 10 power of negative 6. Notice the negative signs for the x squared term. This indicates that the rate of increase in debt slows down as the number of cases becomes very large, which is an important insight. Now, let's turn to the graph of our quadratic model. Here, the x-axis represents the total number of dengue cases and the y-axis represents the total number of deaths. The red curve is our quadratic best fit line. Overall, the curve shows an initial increase in deaths as cases rise, but the slope gradually flattens. This suggests that while higher cases generally lead to more deaths, the relationship isn't strictly linear. For outliers, some points like week 4 with 2,781 cases and 7 deaths lie significantly above the curve. This could indicate weeks with unusually high mortality rates, possibly due to delays in healthcare response or other external factors. And lastly, error analysis. The magnitude of the error vector for the quadratic model is 6.46, which is lower than the linear model's error of 7.97. This confirms that the quadratic model fits our data better. For example, in weeks with fewer than 2,000 cases, the model predicts deaths fairly accurately. However, as cases exceed 3,000, the predictions become less precise, highlighting the complexity of the relationship. So we're moving forward to error vector analysis. How well does this model fit the data? We calculate the error vector E, which is the difference between observed deaths Y and predicted deaths MV. So E equals to Y minus MV. For example, in week 4, we observed 7 deaths but predicted 3.84. Their error is 3.16. In week 15, observed 1 death but predicted 0.09. The error is 1.09. We compute the Euclidean norm of E and found magnitude E equals to 6.463.
Standard cubic equation for each coordinate is y equal to a plus bx plus cx squared plus dx cubed. So to get the best fit cubic curve, we need to use the least square solution, which is y equals to inverse m transpose multiplied by m and then multiply with the m transpose y. The formula to get error vector is E equals to y minus mt. So the error vector for cubic model is 6.360986204. For this slide, you can see our graph for best fit curves against observed data and error vector against x values. For analysis and conclusion, for linear model, the error vector is 7.9722999356. For quadratic model, error vector is 6.463080.738. And lastly, for cubic model, the error vector is 6.360986204. So as we can see here, the best fit curves is the cubic model since it gives the best approximation to the data.